Hello everyone, my name is Devin Xuan and my matrix number is 22004585. Today I'll be presenting our project for KIX2006, which is called Solar Horizon, a sustainable solar energy infrastructure. For our assignment, we have a total number of 16 mates, which is JIUN, Xiangyue, Tan Hongjun, Devin Xuan, which is me, Tan Horng, and Xin. In Malaysia, petroleum and natural gas were the main energy sources in 2019, each accounting for over a third of the country's consumption. In 2016, Malaysia has signed the Paris Agreement, which aims to limit the global temperature rise to below 2 degrees Celsius, ideally 1.5 degrees. In Malaysia, solar energy is very abundant. It is a sustainable, renewable power source with no direct greenhouse gas emissions. Therefore, our project, the Solar Horizon, can help to utilize Malaysia's long sunlight hours coupled with our innovative technology to tackle this issue. For our project, which is the Solar Horizon, it will be located in Kedah. This is because it has a higher average sunlight hours, which is 7.5 hours compared to other regions in Malaysia. In Kedah, it also has cheaper land, which allows us to reduce our budget. It is also far from other residential areas, which helps to prevent disturbances to nearby residents. Our objectives for this project is to enhance high-tech job opportunities, educate the public about solar energy, promote research and development on solar energy, reduce reliance on non-renewable energy, and lastly, our ultimately is to mitigate global warming. For our solar farm, it involves doing something never done before in the industry, which is the inclusion of an auto cleaning and cooling system. This is so that we can clean the surface of the solar panel to remove debris. On the other hand, we also have the periodic spraying of water to reduce temperature and promote the higher efficiency. The benefits are huge, namely to optimize the land use, which allows us to enhance energy yield and can help to contribute to sustainable development. For our project, it involves many risks and uncertainty. The main one being the inclusion of an automatic cleaning and cooling system will introduce unique engineering challenges for us to solve. It also has a potential for budget overruns and funding shortages. The environmental and regulatory risks may be hard for as we also need to solve. For our project, it will take 3 years to complete it and it will cost a total amount of 250 million ringgit. After completing it, our project, the Solar Horizon, will be expected to produce 50 megawatts of power annually. Regular maintenance will be done so that the performance requirements of 50 megawatts of power will be met.
The market feasibility analysis for a 50 megawatt solar farm in Kedah, Malaysia reveals significant potential due to high solar irradiation of 1,900 kilowatt hour per meter square annually, government feed-in tariffs of 40 cents per kilowatt hour, and rising clean energy demand. Existing solar farms in the region have capacities below 50 megawatt and cater primarily to the national grid. While the cost of natural gas electricity generation is currently lower, potential carbon pricing and rising fossil fuel costs could boost solar competitiveness. Targeting the national grid through a long-term PPA with TNB, the project aligns with Malaysia's solar market, expected to reach 4,000 megawatt by 2030. The legal feasibility analysis for 50 megawatt solar farm in Kedah, Malaysia, outlines key regulatory requirements including the Electricity Supply Industry Act 2004, Renewable Energy Act 2011, planning laws and environmental laws. Essential permits include a generation license, feed-in tariff approval, and planning and land use permits. Potential challenges involve securing suitable land, ensuring grid connection capacity, complying with environmental regulations, and securing project financing. Effective legal planning and compliance are crucial for successful project implementation and risk mitigation. The technical feasibility analysis for 50 megawatt solar farm in Kedah, Malaysia involves assessing site suitability based on solar irradiation levels, land area, topography, and geotechnical surveys. The solar energy system design includes selecting appropriate solar panels, evaluating robust mounting systems, and tracking options, choosing efficient inverters. Ensuring a reliable grid connection is also crucial. These factors combined determine the project's technical viability, emphasizing the importance of detailed planning and evaluation to ensure optimal performance and efficiency. The social feasibility of a 50 megawatt solar farm in Kedah, Malaysia involves engaging with stakeholders such as local residents, businesses, government officials, and environmental NGOs. Effective communication strategies include public meetings, community forums, and informative brochures. A social impact assessment SIA evaluates employment opportunities, community infrastructure, health and safety, and land use impacts. A social mitigation and enhancement plan addresses potential adverse effects while enhancing community benefits, ensuring the project's social acceptance and sustainability.
For our components, our budget will amount to 70,169,082 ringgit and 75 cents. Secondly, the salary of the team members will take 475,900 ringgit. Maintenance will cost 14,635,706 ringgit and 77 cents. The total budget, including our land acquisition, civic works, and others, will amount to 290,346,404 ringgit and 55 cents.
In the replacement analysis, the defender represents a conventional solar farm with a capital investment of 241 million. Conversely, the challenger introduces a solar farm equipped with auto cleaning and cooling systems, incurring a higher investment of 289 million due to advanced components and increased installation costs. In operational and management activities, the Defender, a conventional solar farm, incurs 36 million. Conversely, the Challenger, a solar farm with auto cleaning and cooling systems, experiences higher O&M costs of 40 million due to the necessity of regular software and hardware updates, reflecting the investment in advanced technology to maintain optimal performance. The Defender, a conventional solar farm, yields annual benefits of 60 million. Conversely, the Challenger, equipped with auto cleaning and cooling systems, generates higher benefits of 66 million due to enhanced efficiency facilitated by the implementation of these advanced technologies, resulting in increased energy output and overall performance. In salvage value assessment, the Defender, a conventional solar farm, presents a salvage value of 21 million with an annual degradation rate of 0.75% over its 28-year useful life. Conversely, the Challenger, equipped with auto cleaning and cooling systems, boasts a higher salvage value of 57 million with a lower annual degradation rate of 0.65% over its longer 30-year useful life. The Challenger solar farm offers a higher salvage value, indicating potential long-term economic benefits over the Defender option. In the replacement analysis, the Challenger solar farm equipped with auto cleaning and cooling systems demonstrates a higher present worth of 370 million over its 30-year useful life compared to the Defender option. This signifies its ability to generate greater returns and exceed the minimum acceptable rate of return (MARR) of 10%, making it a more financially attractive investment choice despite its higher initial cost. The Defender, with a lower equivalent uniform annual cost UAC of 35 million over 28 years, seems financially favorable. However, the Challenger, despite its higher UAC of 31 million over a 30-year lifespan, offers significant long-term benefits. Its auto cleaning and cooling system contributes to a substantially higher cost-benefit ratio, which will be presented in the next section. Thus, opting for the Challenger proves strategic for maximizing returns, emphasizing the importance of considering both short-term costs and long-term efficiencies in investment decisions.
The benefit cost ratio or BC ratio is a key tool to see if a project is worth the money. It compares the benefit to the cost. Here's why it is important. First, economic efficiency. It helps to put money into projects that give the most benefits for the cost. Second, investment decisions. It shows if a project is worth doing and help pick the best projects by comparing different options. Third, risk management. It checks if a project can work in different situations and helps avoid losing money by choosing project with a good BC ratio. Now we are going to calculate the benefit cost ratio with present worth. And now let's have a look at the conventional solar farm. And first, we are going to assume that the MARR of 10% per year and also the 28 useful in years. And after we plug in the value into the formula for conventional BC ratio, we will get 1.0198 and the modified BC will be 1.0518. Both are greater than 1, indicate that the benefit is slightly higher than the cost. Now we are going to calculate the BC ratio with present worth, but it is for solar farm with auto cleaning and cooling system. And we assume that the MARR of 10% also, and the useful in years is 30 years. So after we plug in all of the value, we'll get the conventional BC ratio is 1.0434 and the modified BC is 1.1197. Both of them are greater than 1 also, so indicate that the benefit is slightly higher than the cost.
Now, let us dive into the calculation of benefit cost ratio with annual worth for both solar farm options. For the conventional solar farm, we assume MARR of 10% and a useful life of 28 years. Using the formula for the conventional BC ratio and plugging in the values for annual benefit, capital investment, and OMM costs, we obtain a ratio of 1.0173. This indicates that the benefits slightly exceed the cost as the ratio is greater than 1. The modified BC ratio also yields a value of 1.0451, which is greater than 1, showing that the project is feasible. For comparison, we also calculate the conventional and modified BC ratios for the solar farm with the auto cleaning and cooling system. For this case, we still assume a MARR of 10%, but with a longer useful life of 30 years. The conventional BC ratio for this advanced system is calculated to be 1.0408, and the modified BC ratio is 1.1122, which are both greater than 1. To determine the most suitable project between the two options, we conducted a financial analysis. The solar farm with auto cleaning and cooling system is the most suitable choice due to its higher benefit cost ratios and modified benefit cost ratios. Both of them exceed 1. This indicates that the benefits significantly outweigh the cost for the solar farm. Furthermore, the BC ratios for the auto solar farm is greater than the conventional solar farm. The conventional solar farm shows slightly lower financial metrics and may not be financially feasible. Therefore, the solar farm with auto cleaning and cooling system is the preferable project, offering more efficient solar power conversion and the added advantages of smart automation system.
The risk breakdown structure includes technical risks like design flaws, technology obsolescence, equipment failure, operational efficiency, and maintenance issues. External risks encompass natural disaster, weather conditions, environmental regulations, and market price fluctuations, while organizational risks involve funding shortage and cost overruns, while project management risk includes construction delays. The risk assessment entails identifying potential risk events across technical, external, organization, and project management domains. Each risk event is evaluated based on its likelihood, impact, and detection difficulties. This comprehensive analysis aids in understanding when these risks might occur and allow for proactive mitigation strategies to be implemented effectively. The risk survey matrix, using failure mode and effect analysis (FNEA), combines impact probability and detections to assess risk value. Based on these assessments, risks are categorized into red (major), yellow (moderate), or green (minor) zones. These help prioritize mitigation efforts, focusing resources on addressing high-risk areas to ensure project success. The risk response matrix delineates strategies to handle identified risks, comprising response actions, contingency plans, triggers for activations, and assigns responsibilities. It provides a structured approach for addressing potential threats, ensuring timely and effective mitigation measures are implemented to minimize negative impacts on the project's objective and outcomes.
And now I will talk about resource allocation and scheduling. First of all, work breakdown structure overview, which is the WBS, and our project includes 8 phases, which I will explain the details of it later. And our project is start from 1st January 2024, and the project will be done by 5th August 2026. This is the project network diagram of our project. Move on to project schedule. We have total of 8 phases, and first is project initiation and planning, which took 65 days to complete. And this is also under project initiation and planning. Phase 2, preliminary assessment and risk identification, which took 65 days to complete. This is also under phase 2. Phase 3 is system design process, which took 66 days to complete. Phase 4, procurement and logistic of required equipment, which took 66 days to complete. Phase 5, which is the main part of this project, installation of solar panel, and it took 152 days to complete. And phase 6, AC cabling and other electrical connections, which took 66 days to complete. Phase 7, which is testing and commissioning, which took 65 days to complete. The last phase, which is maintenance and future support, which took 70 days to complete. That's all about our video presentation of this project. Thank you.